Good afternoon, this is Schweitzer, and this is a short little video on titrations and neutralization reactions. The name of this process is commonly referred to as a titration. What is a titration? And a titration really can be used in many different ways. The one way that I've heard of a titration being used is a friend of mine is a sleep sonographer, and they would take people, pretty common nowadays, and they would bring them in and they would test them sleeping, and they would track their sleep. And then her job was to increase oxygen to the person's brain, and while they're sleeping, they called it titrating with O2. So they would essentially be tracking the blood level of O2, and they'd be adding it until it raised up to a certain point, and then that they called titrating. So they're matching one input to another input. So there's an example of titration. Um, Another example here, with the way we use it here, titration, is to match one solution to another solution. And in a titration, we call it titration. So, what can it do for me? Well, if I have one titration solution and I match it to another solution, I can compare their concentrations, or I can use one solution A to find the concentration of solution B. That is how a titration works. So what can it do for me? It can help me find an unknown moles. So if I want to figure out in a solution how much stuff is located inside of a particular solution, then yeah, I think that's pretty common situation. We're always using ways to find out how much stuff is located in things. It could be lead in water, lead ions in water. It could be, um, it could be certain amount of bacteria or some sort of germ, or could be, that being said, could be a virus in a certain blood area. It could be antibodies. Literally anything that's in a volume, I want to be able to figure out what's inside of it. They could use a titration to do that. Um, okay, so if I know the moles, the number of individuals in a solution, a couple of things that we typically solve for this. One is molarity. Molarity, capital M, is equal to moles per liter of volume. And that's going to be the most common thing we'll do with that in this particular section. So we're looking to determine an unknown molarity or an unknown concentration. All right. Okay. Quantitative versus qualitative. You should realize that the difference between the two terms are. Okay. Qualitative is one version, quantitative is another one. Let's say, for example, qualitative. Qualitative would be something that's either a yes or a no. Sometimes I like to make the sort of comparison. Are you pregnant? Yes or no. There's no in between. Okay. Sometimes for qualitative testing, they want to know, so for drugs, if you're taking some sort of illicit drug, does the um, government or police care how much you're taking these drugs? No, either you are or you're not. You either test positive for drugs or you test negative for drugs, and that's it. Now, there is differences here. Quantitative would be a certain numerical level of concentration. So now we want a number expressing that concentration. Now, for, let's say, for example, alcohol. Um, so alcohol, if you're an adult, there is a legal limit in Wisconsin of 0.08, and that is the amount of blood alcohol level. Okay. Now, for you guys, for young underage people, it is 0, no tolerance, 0.00. So again, you could just use a qualitative example for this. Yes or no? Do we care how much you have? No. But for an adult, it is needs to be quantitative to be able to compare that number. And then at that point, if you're over that amount, if you're 0.01, or so let's say 0.1, they might, a prosecutor might say, okay, use the number of times you're over, 0.2 or 0.3 to sort of punish you to a greater extent if you're over the legal limit by even more. Again, these are all examples of quantitative results. We're doing titrations. Titrations are a quantitative result. We want to look not just look at is something present, but how much of it is present. In fact, we aren't even looking to, we can't really identify what's present. We already know what's present. We want to know how much is present. So that's a little bit different story too, is to identify unknown versus identifying the concentration of a substance, of a known substance. So we're going to identify the concentration of HCl. What's unknown about the HCl? The identity is not unknown. We know it's HCl. We want to know the concentration of that substance. So what do we need if we have a solution here? What do we need to find the unknown concentration? Well, molarity is moles per liter. So I need two pieces of information to find this out. So I need to know the volume of this solution and, different ways to record this volume are much, some are better than others. We would never use a beaker to solve for that value. So typically, for our purposes, a graduated cylinder is probably the minimum level of accuracy that we'd want to use to measure that volume. Okay, there are even better ways, but the graduated cylinder is our standard way of doing that. Never use the beaker. Okay, now, so I got that, check, I've measured my volume. And then I need to know the amount of stuff that's in there. So how many actual particles are in there? Typically, we would express this in moles. Okay, so a quantitative way of measuring these things, and then if I know those two pieces of information, I can get them what's called the molarity, and then I have the concentration. Okay. All right. In order to determine an unknown, you must have a known to compare it to. Have a known to compare to. All right, so a little bit of wording issue there, but either way, this is a really big deal here. Okay, this is I would call a bedrock of science. Okay, and this is something that, for example, used for drug testing all the time. Major League Baseball, MLB. This is something I would typically talk about here. Ryan Braun was convicted of performance enhancing drugs. So he had to go and they took a urine sample from him. And initially he was sort of let off because someone took a urine sample and took it home and put it in their refrigerator and left it there for the weekend. Now that's not part of the standard protocol. And he got off because the science was the actual connection wasn't made anymore. So the known that they're comparing it to wasn't left in the refrigerator. So and wasn't sitting next to the guy's broccoli. So who knows? Likely nothing happened, but you never know. So they have very strict procedures that you follow to make sure your known is exactly what we think it is. So the procedure is just as important as the stuff you're testing. It has special containers that were rinsed specially, and they were collected in special ways, stored in special ways. Everything is to the exact specimen's detail. So your known is always the same. And then we're going to compare it to this thing here to our unknown. And if they match, then we know they're the same thing. Okay. Now, how does this work in chemistry? Okay, and this is pretty common. Okay, this whole idea of known unknown is everything from drug testing to cancer. They know if they take a cell and they stain it a certain way, and you look at it a certain way, and it looks like X, Y, or Z, then this is a result that we know. Everything we're doing is comparing knowns, unknowns, all the time. All right, so in our particular known unknown, let's just say our unknown is HCl of unknown concentration, and we have NaOH of known concentration. Okay, now I'm showing the particulate particles here. We don't see those. Okay, all we know is we see a liquid and we see a liquid. Okay, now the known concentration, this known here tells us about that concentration. All right, so I'm going to take these guys and drop them in here. Okay. Every time I take one of them, you should note, very important, that this reacts, one of these guys can react with one of these guys. So I take an NaOH and I react it with drop it in, okay, and it reacts with one of these guys and knocks it out. Now my pH meter is showing very acidic right now because I have all this acid here. So let's just say this is my first point right here. And then as I'm dropping in my liquid, these guys get sort of taken out. This guy drops in, and we knock out another one of these guys. And of course, base added, pH, I start to get a little bit more approaching neutral because I'm losing, let's say that's neutral. And then I take another one, drop some more in, knocks out another one, and I start getting even closer to neutral. And then drop in some more. Okay, again, I'm just dropping it in here and knock on another one. There we go. Getting closer to 7. And finally, the last one gets dropped in, and I knock out my last guy, and lo and behold, right now I am at 7. And I have this little graph that looks like this. Okay, so at that point, if I can figure out how much of these I added 1, 2, 3, 4, 5. I added 5 of my OHs, which means that right now there's none in there because they're gone. But I know that if I added 5 OHs to get to neutral or neutralize, what we call the equivalence point, I'll talk about that in a moment. But if I add 5 OHs based on the 1-to-1 ratio, that if I had 5 of these, then there must have been 5 of those originally in the solution. And I know if I keep going, this thing's going to just keep going, getting more and more basic, because now if I drop another one in, there's nothing for it to react with, and now I'm on the basic side. And if I keep going, my graph will start to look something like this. Okay, and this is a pretty standard titration curve, and it spikes at what we call the equivalence point. Let's write that out here. It spikes right there, we call the equivalence point. And that's where your moles of your H plus equal the moles of your hydroxide. They're matched. Okay. Now again, if I kept going, I had just have more and more hydroxide collected, and my experiment essentially is over. Okay. So this is a visual of what this is happening here. Keep in mind, I'm showing these little particles here, but you really don't know. Okay. All right, unless you have some way of tracking. Now, my pH meter here is playing a very important role as to telling me, if you didn't see these little pictures here, as to when you actually reached the matching point. Okay, so we'll start weaning ourselves in that direction. All right, so for example here, I'll take, and I have a solution here that is considered um, acidic, and therefore we'll put ourselves a little point right here, okay, as far as being acidic. And every time I drop one of these guys in, okay, I'll take one of these guys, and I'm going to grab my pen here, I'm going to pour some in, drop it in here, and what happens? I get a water produced. Again, why was that thing producing a water molecule? Well, because there must have been an H plus present. So there must have been an H plus in that solution. I showed on the last slide, but I'm not showing it anymore. All right, and let's do this quickly here. Okay, so I added hydroxide, and sure enough, now I'm getting a little bit more towards neutral. Okay, so I drop another one in, and I get another water molecule formed because there must have been an H plus there. And of course, I'm getting a little bit more closer to neutral. I drop some more in, and sure enough, I get another water molecule produced because I must have an H plus present there. Now keep in mind, I'm just working my way towards being neutral and getting ever so close. Add in one more hydroxide, and I am going to get one more water molecule. And of course, at this point, I get to my pH of 7, and I realize that, okay, at this point, I'm now stopping. So I stop. It's okay, well, I'm now at a pH of 7, so let's hold on for a second here. I'm at a pH of 7, so what is my original concentration? Well, they're all gone now. So really we want to look at to get our original concentration. Now this beaker, okay, keep in mind, let's just say you want to test a sample. And let's just say you have yourself a big lake, okay, maybe Blackfire Lake. And are you going to be able to test the whole lake? No, you can't test the whole lake. So what you do is you go out and you go in the lake and you sample yourself a sample. And you bring it in a container back to the lab. So that sample is representative of the lake, or at least area of the lake where you were, right? If you take a sample right by the edge of the shore, maybe it might be different than if you were out in the middle. So you'd be kind of aware of that. But that sample is proportional to the area where you measured. You don't, if you have a pool at home, you don't test the entire pool. My sample actually gets destroyed while it's being tested, being neutralized. So really what I want is the original, to find the original concentration. Okay, the original molarity is equal to the original moles, okay, original moles, divided by the original volume. And that will give me my original molarity. So this crude example here says, I would say, okay, I titrated to a pH of 7 or neutral. So at that point, I want to stop. How many did I add? Well, I had 4 equivalent, 4, or I would want the moles of the hydroxide. Now that's hydroxides. Is that what I want to put here? Do I want to put the 4 hydroxides here? Well, it turns out that for every one of these guys, there was one of these present. So really, previous to this, there was 4 H pluses that were in there originally that my 4 hydroxides reacted with. And then I would want the original volume before I even got started. So whatever that happens to be. Okay, you want to record that even before you start titrating. You'd want to record that. So I would take my original volume, original moles, divided by my original volume to give me my original concentration. That's kind of important. Okay, so that's kind of a visual of how this thing happens, how it works. Okay. All right. Again, I have my known, which was the 0.1 molar. Okay. And I have my unknown here. So just a quick little, one more little thing here about this is how would I get the amount. I wrote 4 down here for this guy, but how would I actually get that number of particles? Well, I want moles of this guy right here. So how would I get the number of actual hydroxides I added? Well, that would be moles. So molarity equals moles per liter. And so molarity times liters equals moles. All right. So it tells me that, or know already, that this volume is 0.1, and I would need to know the volume that I added of this stuff into here. Now here I counted individuals, but I need to know the volume that I added. If I know the volume it took to get to my pH of 7, then I would know the moles it took to get to 7. And of course, this is the moles of hydroxides. So plug that guy in there. Keep in mind, we got to use liters. And if I knew that, then I could have the moles of OH, which equals the moles of H pluses that were originally present. And of course, at that point, I can do moles of H pluses divided by the original volume to give me my original concentration. Okay, that in a nutshell is my calculation as well. All right, let's try another example here. All right, how do we physically do this, in lab? Okay, so we're going to have likely a lab video that you're going to be in lab. You could try it out, or you'll see something at some point to what this looks like. Okay, so a few things. One, we have a device up top here. Looks just like that. It's got a little valve on here. Of course, the valve, be aware, if the valve is, as it comes down here, it's a glass tube. It's been around for a long time. And they have this spout here with a little valve. If the valve is perpendicular, then it's closed. And if it is vertical, in line with this thing, then it's open. And really, this is just a very specialized distributing device, or the way to measure out what you're adding. So all they do is they have little markings on here. And the way you would know how much you added is every time we run a lab, we'd have a start, a finish, and then we'd have an end. Get in the way here. Okay, remember in that last slide, one key thing I needed was the volume. Okay, down below here, I needed the volume of my known. That was pretty important. Okay, and I need the volume of everything. I need the volume of known and the volume unknown. But I need the volume I know. And that is given to me via what we call the burette. B-U-R-E-T-T-E. And I'm going to just dispense this thing until I reach my equivalency point. And then, at that point, I'm done dispensing. Okay? So we put our known in the burette. And I dispense it. And I track my volume with this little table here. Okay. So I put my unknown here. And I also want to know that volume before I get started. So all I need to know about this guy is the volume when I get started, before I get started. All right. So again, key terms here. Equivalence point is when you've added enough equal amounts of both acid and base. And then how do I know when I've reached, how do you know if or when you have added enough to reach your equivalence? So once again, I have my unknown here, and I have a base this time. I start dropping in acid. Okay, so my H plus ions drop one in, and it neutralizes. Drop another one in, and it neutralizes. Drop another one in, and it neutralizes. Drop another one in, and all of a sudden, it's done neutralizing. How do I know? Well, you have two methods here. Okay, one is a little more complicated and hasn't been around nearly as long, and that is going to be the pH meter. And we're keeping it simple here, but we'd be kind of looking for pH, again, simple, a pH of 7. Now, that's not always the case. For us, it will be, though. It means you're neutral. Or you could use an indicator. Okay, what's an indicator? This is how they did it before we had electronics. So an indicator, the most common indicator, and also conveniently the longest word I can successfully spell half the time, is phenolphthalein. So a chemical indicator is simply a chemical that changes color with pH, with a change in pH. It's not acidic itself, it's neutral itself, which is kind of important for an indicator. We wouldn't want the indicator to affect our answer. So the most common chemical indicator is phenolphthalein. And it makes a pretty, although it's not perfect, okay? Got a pretty distinct color change between neutral and basic. Acids are typically thought of being clear. Bases are typically thought of being pink. Right around 8.7-ish, it flips, and it flips pretty good. And even slight pink. So how do you know if you're at your equivalence point? Well, what you would do before you get started on this last one is you would actually drop in, before you get started, into this beaker just a couple drops of phenolphthalein, okay? And then it's going to change color when it changes. So if you go from clear, if you're clear, means that your beaker has an acid in it. So it'd be clear. And you're dropping in a known hydroxide. Well, then you look to see when it turns pink. And you wouldn't want to keep going. Any sign of pink that just sticks around, you'd want to stop. At that point, you're awfully close to your equivalency point. But if you're titrating a base, okay, then it's going to start out pink, okay, and you're going to be dropping in hydroxides, here, H plus ions, okay, and you drop them in, it's going to turn clear, and the last sign of your pink disappearing, and you're awfully close to the equivalency point, okay. Now pH meters are a little bit more, considerably more accurate, but with that being said, this thing works very well, okay. It just doesn't, indicators just don't work for everything. So that's sometimes how we know if we've reached our equivalency point. And if we were doing this in lab, we would use phenolphthalein. Okay. All right, next up. So sample question. This is how we would really describe on a the most common typical type of problem that you could have involving a titration. Okay. If you're walking to class on the day of a quiz or a test and you're thinking about, titrations, I wonder what type of problem there would be. This is the type of problem that's most common. So let's see what we got here. And now we'll also be walking through the calculations on this. And so far, everything we've done so far has been qualitative. Now let's get straight into the calculations, how we actually do this. So an unknown base is being analyzed for its concentration. So the base is unknown. Sometimes we use this table right here. Okay. Unknown. So right away I might put a B here for base, just to remind myself. Therefore the known is the acid. And what's unknown about it? Its concentration is unknown. We know it's a base. We may even know the identity of the base. We just don't know the concentration. A 50 milliliter sample of the known is measured using a graduated cylinder of the unknown. So 50 milliliters of the unknown. So here's my standard data table for this, and kids really like this. So unknown volume is 50 milliliters. So 50 milliliters here. And of course, I would typically use liters. I might just convert right away, or I might just make an indication for myself. That's 0.05 liters. Okay. An unknown acid, a known acid of 0.1 molar HCl. So right away, okay, this is 0.1 and is being used to titrate against. Okay. 2 drops of phenolphthalein, that's my indicator. okay, it doesn't take much, this stuff is super concentrated, is added to the base and turns pink. Okay, so this thing here is my unknown, and I drop it in and this stuff turns pink. Okay, so right here, I don't know if I can do a very good job of that, but we'll just maybe do this here. This stuff turns pink right off the bat. And why is it turning pink? The indicator's in there and it's causing it to turn pink. Okay, so let's see. After adding 25 milliliters of the known acid, the solution turns clear. So what we're looking at here is this. They started titrating into this thing, okay, with their burette, all right, a little valve here, and they're dropping in the H plus ions. And what they did was they measured here the start, and they measured the end, or the finish, sometimes they call it finish, okay, and what's the change? Now again, it doesn't matter where we start on the burette's got a lot of numbers on it, and all they did was mark out a start point, and they're saying it could have been started at 5 milliliters, okay, but then it ended at 30 milliliters as far as the markings were concerned on here. Started at 5 and it went to the 30, and therefore the difference is 25 milliliters of actual known was added. And that's what we put right there. The known volume comes from the burette, and it's 25 milliliters, 0.025 liters. All right, so now here are our questions. How many moles of acid were added? This guy. Okay, let's do that math. I want this guy right now. So it's going to be 0.1 equals, now molarity equals moles per liter, right? So it's going to be 0.025 sulfur moles, and it's going to be multiply across 0.0025 moles. So this is 0.0025. Okay, check, done. How many moles of base were neutralized? Well, this is the part where the known and the unknown compare. They're the same, okay? If we couldn't make this connection, equivalence point, then we'd have no comparison between the two. So this is what we're using, 0.0025. Okay. What was the final volume? Well, the final volume, well, I started out with 50 in this beaker, and I added 25 to it, okay, which gives me 75 total at the end, okay. So in the end, I got a larger volume and say 5 milliliters, and there's just a bunch of waters. There's 1, 2, 3, 4, 5, 6, 7. There's 7 waters that were produced. Those are my waters. So this equals H2O. All right. What was the final volume? Well, the volume was 75. But I don't care about the final volume. This is not something that I really care that much about. Okay. Let's get rid of that. Okay, I don't care about this very much. I want the original volume. The initial volume of the acid was 25 milliliters. So let's change that because I want base on here. Okay, that's what we're looking for. The original volume was 50 milliliters. Okay, or 0.05. What's the original concentration? Okay, so I'm going to take the original moles, divide by the original concentration, original volume, gives me the original concentration. Again, this is all kind of destroyed now, but that doesn't matter. Again, that sample is from a bigger something else. All right, so I'm going to go with let's do this here, 0.0025 divided by 0.05, and I get 0.025. moles per liter. And that is my answer. The table is just a table. Make sure you show all the work necessary to show how the tables originated. Just filling a table out does not cut it. If you're using estimations, then make a sentence about how you estimated things. All right, next one. Okay, is there a relationship between the quantity of the known and the unknown? Very often there is, and very often you want to be aware of this. Okay, let's look at an example here. 20 milliliters of an unknown acid. Okay, so 20 milliliters here is neutralized by 20 milliliters of a 1 molar base. This is 1 molar, this is 20 milliliters. So it took 20 milliliters of these to match each other. So this and this are now equal. Well, if you have equal moles on equal volumes, then the molarity should be equal. So if the volumes are equal, then the concentrations are equal. That's important to realize. Okay, let's look at the next one. A 5 milliliter sample of unknown base, this is 5, was neutralized with 10 milliliters of 0.2 molar. 10 milliliters of 0.2. All right, so in this case, we have the same number of moles. All right, so the same number of moles in 1/2 the volume. So that means this stuff must be twice as concentrated, 0.4. That's an important relationship to see. Okay, let's try another one. Okay, what if I have 10 milliliters sample of unknown HCl is neutralized, so I got 10 milliliters of unknown. Okay, 12 milliliters of 0.2. Make sure you just keep the volume with concentration. And it wouldn't matter which side it's on. So make sure you got those two locked up that are correct. So these are the same. So one question we commonly ask here is, who's more concentrated, the unknown or the known? The acid or the base? Now in this case, my 0.2, this guy is the base. And this is my acid. Okay? So same number of moles in a smaller volume means this guy should be larger than 0.2. That's my answer. Good multiple choice question there. Let's take a moment and actually calculate it. Okay, so this is going to be 0.012 and 0.010. And let's take a moment and actually calculate out what the actual answer is. I know it's bigger than 0.2. Molarity equals moles per liter. 0.2 equals 2, the concentration, and then 0.012 solve for the moles. And 0.2 times 0.012 equals 0.0024. 0.0024. And that is going to be my number of moles. These are going to be equal, 0.0024. And take that and divide by the 0.01 liters, and we're going to get our new concentration. All right, and divide by 0.01, and I got 0.24. And this is 0.24. Now, a lot of times I can come really close to estimating just off proportions, but there you go. Okay. So lots of stuff there, and if this makes sense, then you're on the right track. Thank you very much.